Hello students, in this video we are going to see that how we can find pKa of a compound using electrochemistry, specifically the cyclic voltammetry. In my previous video we have seen that we can find out the value of pKa using electronic absorption spectroscopy. But there are other techniques through which we can find out the value of pKa, such as CV or some other electrochemistry techniques like differential pulse voltammetry or square wave voltammetry. In this video, we are going to see how we can use the cyclic voltammograms to find out the value of pKa. pKa is the pH value at which protonation and deprotonation occurs at equilibrium with each other. In terms of electrochemistry, it will be a point at which the only electron transfer will be taking place in your ionic solution. So in order to find out the pKa of your compound, you need to make the solution of your compound at different pH values. This can be done by making the buffer solutions at different pHs, such as ranging from pH 1 to pH 12. And then you can make the solution of your compound in that buffer solutions and take the CV of your data or the cyclic voltammetric graph of your data. Here on this graph you can see there are the CVs of one particular compound at different pH starting from pH 1.3 to pH 8, but you may need to take the CVs of your compound till pH 12. But I have shown here for the compound only till pH 8. So you will see that the peak's position, this one is the anodic peak and the lower peak is the cathodic peak. And these peak positions, they are changing their positions with respect to the pH. As you are changing the pH, the peak position as well as their current intensities are changing. So this change is because of the fact that at different pH values there is a different involvement of the number of protons in the redox process of that compound. So now once you have this data of the CV, that is the current plotted on the y-axis and the voltages on the x-axis, we can convert it to find out the value of pKa. Let's see how we can do that. We can take one of the peak position, that is either the anodic peak or cathodic peak. Like in this figure again, if you see this black line, this one is the anodic peak. Let's suppose I choose this peak as the peak which I am going to use for finding the pK of the compound. So what I will do, I will measure the peak potential, that is the peak potential which is on the x-axis for this peak at pH 1.3 and then at pH 2.1, pH 3.1 and so on, and I measure the peak potentials of this peak at different pHs and make a table out of this data. The next thing is that what we do is that I plot the peak potentials of this peak versus the pH of the solution. So pH is plotted on the x-axis 2, 4, 6, 8, 10 and 12 till 12, and I'm plotting the peak potential which is EPA, anodic peak potential, on the y-axis. So you will see that the peak potentials are changing with the pH. The third step is that we are going to draw the straight lines connecting these points. Sometimes you get a straight line, one straight line for that data. But in other kinds of experiment, you will get two lines, or maybe you will get more than 2 lines in this plot. So here from this data, I see that I have one straight line connecting these black points till around before pH 8. And then you see there is a drastic change between these 2 points. And then the peak potentials are almost constant after that pH, from pH around 9 to pH 12 something. So once we have the straight lines drawn, I will draw a straight line for these points separately and for these points separately. And once you have 2 straight lines, what you will do, you will take the mean of this point, the last edge of the first straight line, and the start of this straight line. You will take these 2 points and take the mean of the potentials at this point. That is, the potentials are here. So So you take the mean of the potential at this point, and then let's suppose the mean of potential is coming at is something like 0.37, something like this. Then you draw a straight line from this potential to intersect this line, and the corresponding value on the x-axis to this intersection point is the value of the pH, which is the pKa of your compound. And in this case, it comes out to be 8.83. So this is the pKa, a point at which the protonation and deprotonation of your compound is taking place simultaneously at equilibrium with each other. So this is how you can use CV data for determining the pK of the compound. If you like this video, please like and subscribe. Thank you.